Welcome to the next session, which is planet formation, migration, and something else. Evolution. Right. So we have 4 talks in this session, and I'll be the moderator. I'm Renu Malhotra from local place, Lunar Planetary Laboratory. And let's see. The first speaker is Stephen Lee. He's talking about angular momentum drain, despinning embedded planetesimals. So you have 12 minutes total, 9 minutes for your talk.
Is it working? Can people hear me? All right. So again, hello, thank you. I am Stephen Lee. I'm from the University of Rochester, and I'm going to be talking about angular momentum drain, despinning embedded planetesimals. So planetesimal formation, depending on how you're forming, can have an angular momentum problem. If you're going from streaming instability or from turbulent vortices, you're going to have a large cloud of material that you need to coalesce into a small central object. And that's always going to have the need to get rid of angular momentum. In the simulation on the right from Nes you can see that they have exactly that. They have a giant cloud, and then it coalesces into 2 central objects here. So some solutions to getting rid of the angular momentum of the cloud. You can have binary formation, where instead of just a single planetesimal, you put the angular momentum also into their orbital angular momentum. You can be ejecting objects, so forming a bunch of planetesimals and then having gravitational encounters and throwing them out as the process is happening. Inefficient collapse, where you have a bunch of leftover material, which is even here in this simulation. But the method that I'm interested in is looking at impact ejecta. So to talk about impact ejecta, you have to talk about crater scaling laws, because that is how you're actually going to be getting the ejecta from your impacts. So in 2011, Housen and Holsapple came up with normal impact crater scaling laws, and they based that off of impacts ranging from 2 to 7,000 meters a second. And these scaling laws give you the crater radius, the ejecta velocity, the mass ejected above some velocity. But most impacts are not going to be normal impacts. They're going to be coming in at some angle. In 2022, Radican et al. Converted these into oblique impacts. So these are the same mu C1K R functions as above from Housen and Holsapple, except for there are these zeta and theta terms that they add in, where theta is the impact angle on the actual projectile coming in, and then the zeta is the azimuthal angle around the crater. So these K and R equations were verified in 2024 from Quillen and Duran for low velocity impacts. And low velocity impacts specifically are what I'm interested in as well. So why am I interested in low velocity impacts? Headwind velocities tend to be quite low and consistent throughout the disk, on the order of about 10 to 100 meters a second, which is similar for turbulent eddy velocities in disks. So there's potential for lots of impacts at these lower impact velocities, and therefore potential for lots of mass at these low impact velocities. So something else we have to consider is which regime these impacts are happening in, because you can have impacts happening in the crater regime or the strength regime. And this is a very popular topic to a degree right now, because it's a bit tricky to pick which regime it's in. There have been a lot of artificial impacts that have been saying where the observed cratering seems to be showing that there's very low surface strength on the order of about 1 Pascal. And that then would be putting you into the gravity regime. You can have bulk cohesive strengths due to van der Waals forces, which will put you at about a 25 Pascal strength. So those sort of your lower boundaries that you can have. Now, the thing to note here is that this is for high velocity and large projectiles, and those are going to be falling into the gravity regime. But something to note, though, is that grain growth from coagulation fragmentation models tend to scale up to about a decimeter, so about 10 centimeters. And headwind velocities, as we were previously mentioning, are about 1 to 100 meters a second. On the graph on the right here, I had plotted the transition region between the gravity regime on the left of the diagonal lines and the strength regime on the right here. So as you decrease the projectile velocity, the strength regime takes up more space. Also, when you're decreasing the planetesimal surface strength, you are also increasing the region that the strength regime is going to be operating in. So this is for when you have a projectile at some radius and you're decreasing that radius, that's going to shove the regime transition point over to lower surface strengths for planetesimals. So for low velocity, small projectiles on planetesimals, cratering is likely to occur in this strength regime as opposed to the gravity regime that we see in these artificial impacts. So something else that I took into account was the fact that planetesimals are going to be rotating. So when you have your projectile velocity, that's going to be from the inertial frame, but these crater scaling laws are in the surface rotating frame. So when you're converting from the inertial frame into the surface rotating frame, it's going to impart some impact angle, as well as it's going to have some slight variation on the actual impact velocity. But then you have to go back into the inertial frame, and then something to note here is that the downrange ejecta does not always align with the planetesimal rotation direction. So sometimes the rotation is going to be giving it an extra kick and an extra bit of velocity, whereas other times when you're on the leading side, it's going to make it as though it is ejecting at a lower velocity. So that is going to be a very important difference that we have to be taking into account. Now, just for some context, I defined a angular momentum transfer as well as a mass transfer efficiency for a distribution of impacts. Because I'm not looking at just one impact, but this is an example of a single impact. But I'm taking a distribution of impacts across the entire planetesimal surface and then integrating all those up. So the mass transfer efficiency is looking at the average ejecta mass that escapes and then dividing that by the average projectile mass. And if that is above 1, we are in an erosional regime because we're ejecting more mass than the projectile is putting onto the planetesimal. And if you're below 1, you're accreting material. Now, for the angular momentum transfer efficiency, it is similar, but a bit bigger of an equation. Not really, though. It is looking at the average change in angular momentum as a fraction of the initial planetesimal angular momentum. And you get the change in angular momentum by looking at the linear momentum of the ejecta velocity in the downrange direction. That is this inner term here. And then you take your cross product with your radius just to get an angular momentum, but we're only looking at the component that is aligned with the planetesimal spin vector, because in this study, I was only looking at the angular momentum transfer that is either spinning up or spinning down the planetesimal. And something to note is that I have a negative here in this equation to say that spin down is a positive value and spin up is a negative value. Now for the actual findings is that there's a lot of graphs here, so let me explain them a little bit. On the left here, you have the angular momentum transfer efficiency, and then you have on the right here of the left half, you have the mass transfer efficiency, and then the same thing on the other side. But on the top left, we're varying the density ratio of the projectile and the planetesimal. On the lower left, we are varying the planetesimal strength. We're then varying the headwind velocity and the planetesimal spin. So the main takeaway here is that a lot of these values tend to hover around about a value of 1, where you end up being able to drain the entirety of the planetesimal's spin from one planetesimal mass's worth of impact, which you're probably not going to have a full planetesimal mass of impact. So, but it tends to be about 1, with the variations occurring in the density ratio primarily, as well as the headwind velocity. You get a lot of variation and dependency on those values specifically. For the mass transfer specifically, we have the erosional regime located in red and the accretionary regimes in green. So for a lot of larger planetesimals, we end up in the accretionary regime. But even for the lower radii planetesimals, we still have plenty of cases and scenarios where we are in the accretional regime. So something else to consider is that there's a velocity gradient that you might expect, because the ambient environment is not just completely static and in line exactly with what is happening. You can get a linear gradient across where you might have a slightly higher projectile velocity on one side and a slightly lower projectile velocity on another side of the planetesimal. So taking this into account, there's no difference. It did not matter. but it's something that we at least tried to take into account. But for the size that a planetesimal is, the amount of space that you can expect impact projectiles to come from, there's not enough of a projectile velocity difference to make an actual impact on the transfer ratios. So I ended up talking a bit quick. Sorry. The main results from this, though, were that there is a narrow regime where angular momentum transfer is quite significant. And in that regime, we can estimate around 30 to 50% of a gravitationally bound cloud's angular momentum to be shed from the planetesimal via impact ejecta. This, of course, was not just me. I'd like to thank the collaborators and my advisor for helping going through this paper. And it is a published paper, so you can find it if you do really want to. Thank you.
Dave, go.
Hi, this is very interesting work. I'm wondering, so if I understand, one of the things you're tracking is the spin states, right, of the bodies. Do you account for the maximum spin rate before breakup as like a upper limit on how much angular momentum you can actually put into the spins? So that's what the omega max is.
Yeah, so this is varying the planetesimal spin where omega max is at the planetesimal is at the breakup velocity for the density strength of the planetesimal. We did not take into consideration spin of the projectile. There is some work, I believe, that has been done for impacts with spinning projectiles, but that was not taken into consideration in this study.
We have time for another question. Okay,
for an easy question, you can ask about what
here's
the
an
big
easy
dip was.
question. So what can you predict for spin orbit alignment, anti-alignment on average, statistically?
So we didn't necessarily look at the large statistics of what we'd expect from it, but going through the estimate, I have a bunch of backup slides. The estimate is that you end up with about 50%, at specifically 45 AU is where we were testing. So you can get an estimate for the amount of projectile mass that you expect for a planetesimal, and then you can take that ratio, so in this case 0.5, and then you can put that into the findings here to find whether or not you're expecting there to be, like, what percent of the planetesimal spin you expect to be drained from impact ejecta. So in this case, we can expect about, like I was saying, 30 to 50%, depending on the actual values that you are using and plugging in for, say, headwind or the density ratios or the strength.
Okay, thank you. This is it's very important work, and it's observationally important too. Okay, thank you.